All right, today we're going to build a bridge between two worlds you might think are totally separate. Algebra, with all its equations and variables, and geometry with its graphs and shapes. And the name of this bridge? It's the Factor Theorem. And trust me, it's an amazing tool for taking problems that look absolutely impossible and just breaking them right down.
So look, I'm sure you could factor x squared minus 1 in your sleep, right? Simple difference of squares, no problem. But what about this thing? X to the 5th minus 32. Uh-oh, suddenly our simple little patterns don't quite cut it. This is exactly why we need a better, smarter tool to find our way in.
And here's the best part. The key to building this bridge, to solving that problem, isn't about learning some crazy new formula from scratch. Nope, it's just about connecting two super simple ideas that you already know. We're just going to lay them out one by one and build our path to the answer.
Okay, first, let's just rewind the tape a little bit to the remainder theorem. You remember this guy, right? All it says is that if you take a number, let's call it c, and you plug it into a polynomial, the answer you get is the exact same as the remainder you'd find if you divided that polynomial by x minus c. It's a really neat shortcut.
Okay, now for piece number 2 of our puzzle. What's a factor? I mean, really, what is it? It's just something that divides into another thing perfectly. It leaves no messy leftovers, no remainder. The remainder is 0. So we have one theorem all about remainders, and we have a definition that depends on the remainder being 0. I bet you can see where this is going. Let's put them together.
So when we combine those two ideas, we get the Factor Theorem. And it's so elegant and so powerful because it's not a one-way street. It works forwards and backwards, and that's what makes it so incredibly useful.
Now you really got to pay attention to that double-sided arrow here. This is the whole shebang. It's an if and only if deal. That means these two statements are basically the same thing. They're interchangeable. If x minus c is a factor, then p of c has to be 0. And if you find that p of c is 0, then you know for a fact that x minus c has to be a factor. They are two sides of the exact same coin.
And this is where the bridge to geometry gets built. Think about it. What does p of c equals 0 actually times mean on a graph? Well, p of x is just a fancy way of saying y. So we're saying the y value is 0. And where's the y value 0 on a graph? Right on the x-axis. So finding a factor is literally the same thing as finding an x-intercept. A root, a 0. The algebra and the geometry are telling you the exact same story.
All right, that's enough theory. The best way to really get this is to see it in action. So let's run through a couple of examples. We'll start easy and then ramp it up and see how we can use this thing.
Okay, first, a simple check. Is x minus 3 a factor of this polynomial? Now, we could do long division, but why? The theorem gives us a shortcut. If x minus 3 is the factor, then our c is just 3. So let's plug 3 into the function and see what happens. We get 3 cubed, that's 27, minus 4 times 3 squared, so 4 times 9 is 36, plus 3 plus 6. So 27 minus 36 is negative 9, plus 3 is negative 6, plus 6 is 0.
And since p of 3 equals 0, what does the factor theorem tell us? Bingo! Yes, x minus 3 is a factor. It's a done deal. No guesswork, just a simple calculation.
All right, let's try a more common type of problem you'll see in class. This time, we're given a clue. We're told that x equals 2 is a root. The theorem instantly tells us, hey, that means x minus 2 is a factor. So we can use that to start breaking this whole thing down.
And to divide out that factor, we'll use our good friend synthetic division. So we write down the coefficients. 1 for x cubed. Careful now, there's no x squared term, so we need a 0 as a placeholder. Then negative 7 and 6. Our root 2 goes in the little box. And now we just run the pattern. Bring down the 1. 2 times 1 is 2. Add them up, we get 2. 2 times 2 is 4. Add them up, we get negative 3. One last time. 2 times negative 3 is negative 6. Add them up, and there it is. That gorgeous 0 in the remainder box, just like the theorem promised.
Now that 0 is great, but the real treasure here is that bottom row. Those numbers, 1, 2, and negative 3, those are the coefficients of what's left over. We've knocked a cubic down to a simple quadratic. And a quadratic, well, we know exactly what to do with that.
We can factor x squared plus 2x minus 3 pretty easily into x plus 3 and x minus 1. And once we bring back the factor we started with, the x minus 2, we've done it. We've taken a complicated cubic and broken it down completely into its simple parts.
Okay, now for the real pre-calc challenge.
Here we've got an unknown, k, and we have to solve for it. The logic is exactly the same, we're just working backwards. We're told that x plus 1 is a factor. Okay, wait, red alert. This is where people trip up. If the factor is x plus 1, what's the root? It's -1. So we know that if we plug in -1, the answer must be 0. We just set up that equation, plug in -1 for x, and the rest is just simple algebra. We solve for k and find out it has to be 2/3.
Okay, so you've seen the mechanics. Now let's just add a final polish by going over the most common mistakes people make. And then we're going to look at a truly mind-blowing way this theorem is used in the real world.
This is it. This is, without a doubt, mistake number 1. The sign flip. It's so easy to get this backwards. You have to burn this into your brain. The factor is always x minus the root. So if your root is 5, your factor is x minus 5. If your root is -3, your factor is x minus -3, which becomes x plus 3. You always flip the sign.
The second pitfall is a little more subtle. It's about what that 0 actually means. When you get a remainder of 0, it does not mean that x equals 0. It means the output, the y value of the function, is 0. And what does that mean on the graph? It means the graph has touched down right on the x-axis. You found an x-intercept. So this is all great for your homework. But you might be thinking, okay, but when am I ever going to use this? Well, how about every single time you scan a QR code? Or, if you remember them, every time you played a scratched CD? How do those things magically work, even when they're damaged?
The answer is this incredible bit of engineering called Reed-Solomon error correction. And what's at the absolute heart of this amazing technology? You guessed it, a direct, brilliant application of the factor and remainder theorems.
It's honestly genius. The data in a QR code is actually represented as a massive polynomial. But here's the trick. It's designed from the start to have certain roots. Think of them like secret checkpoints. So your phone scanner knows that p of 1, for example, is supposed to be 0. If it scans the code and gets 0, great, the data's perfect. But if there's a smudge or a scratch, it'll get a non-zero remainder. And here's the incredible part. That remainder isn't just an error, it's a clue. It contains the exact information the scanner needs to find the mistake and fix it on the fly.
So you see, the factor theorem isn't just about finding intercepts on a graph. It's about a fundamental idea of checking for errors and correcting them. It's about data integrity. And that really makes you wonder, doesn't it? What other hidden math is quietly powering all the technology that we use every single day?